In this video, we are continuing our final review and talking about linearization. So the example that I want to look at is the following. Let's estimate ln of 0.9 plus the cube root of 64.5 by using a linearization of an appropriate function at a nice value. Okay, so first thing I want to do is just have you all pause the video and try this on your own first. So pause it for about 2 to 3 minutes to try this question. So 4, 3, 2, 1, pause the video. Pause the video and try this for about 2 to 3 minutes. Alright, so hopefully you've done that. Hopefully you've paused the video to try this. So let's begin by writing down the appropriate function. So looking at this, I see sort of two parts to it. There's this ln part and this cube root part. So I'm thinking I'll need a function of two variables, and I'll make one of the parts of this ln of one variable, and the other part be the cube root of the other variable. Okay, so that might be my appropriate function. And our goal is we want to approximate f of 0.9 for x and then 64.5 for the y. Okay, so we want a nice point, a nice x comma y that's close to 0.9. Let me write that 0.9 a little bit better actually. So 0.9, close to 0.9 comma 64.5. But that's nice to plug into this function that I'm able to plug in easily without a calculator. Okay, so what's something close to 0.9 that I can plug in easily into this ln? Well, it would just be 1. Okay, I know what ln of 1 is. It's 0. And what's something close to 64.5 that I can plug in easily into a cube root function? And that's 64. Okay, so we were looking for something that's close to 0.9 comma 64.5. But that's nice to plug into my function where I can easily do it without a calculator. Okay, so we are trying to approximate f of 0.9 comma 64.5. And using linearization, this is going to be approximately f of the nice value, f of 1 comma 64, that nice close value. And then plus, we take the x partial derivative, evaluated at this point, 164, and you multiply it by the change in x. The change in x from this nice reference point to our point that we care about. And then you do the same thing with the y partial. You take the y partial, plug in our point, 164, the nice one, and then you multiply it by delta y, where delta y is how much y changes from the nice reference point, 1 comma 64, to our point that we actually care about. So if we had a function of more variables, like 3 variables or 4 variables, we'd have a very similar looking formula, except you'd have more partials at the end of this. Okay, so let's start to work this out. So f of 1 comma 64, well, that's ln of 1 plus the cube root of 64. Okay, then I need to take the partial with respect to x, which is going to be 1 over x, and then plug in the point 1 comma 64. So this vertical line is typically notation that we use for antiderivatives, but it's just notation that I can use to indicate, okay, I need to plug in this point into my function. Okay, multiply that by the change in x. So the change in x is how much x changes from the nice, our nice point, which is x is 1, to the point that we actually care about, where x is 0.9. Okay, so that change is 0.9 minus 1, which is negative 0.1. That's my delta x. Okay, so the partial with respect to y is going to be 1/3 y to the negative 2/3. And then delta y is 0.5. That's how much y has to change from 64 to 64.5. Whoops, I forgot to indicate that for my y partial, I need to plug in the point 1 comma 64. Okay, so let's simplify. All right, so ln of 1 is 0, cube root of 64 is 4. All right, so if I plug in 1 for the x here, I get plus 1 over 1. There's no y to plug into. Okay, that's okay. And then times negative 0.1. And then I'll have 1 over 3 times y to the 2/3. And y is 64. And then that's going to get multiplied by 0.5, 0.5. So let's keep simplifying. So we have 4 minus 0.1 times 1 is 0.1. And let's write it as a fraction, 1/10. And then I get plus 1 over, I'll get 3 times, with 64 to the 2/3, we do the cube root of 64. Usually it's nicer to do the root first, because I get a smaller number. And then I raise it to the power. So cube root of 64 is 4. 4 squared is 16. Okay, so 3 times 16 is 48. And 48 times 1/2, because 0.5 is 1/2. Okay, so we got 4 minus 1/10 plus 48 times 2, that's 96. 1 over 96. All right, and from here it's not bad. It's just working out what this is. So I'm just going to tell you what this ends up being. It ends up being 1877 over 480 when I simplify it. And that's my answer. All right, so we have finished our one goal for this section, which was just to do a bit of review for the final from chapter 14, and look at some practice problems. So there's no way for me to review all of chapter 14 in one video. So there's definitely stuff that I didn't get a chance to talk about in the videos for today. Stuff like limits, that was section 14.2, or chain rule, that was section 14.4. So that's definitely content that could show up on the final exam, but I had to pick and choose a little bit for what to include in my review videos. So the problems that we looked at in these review videos don't necessarily mean that these are the kinds of questions that are going to show up on the final. I could definitely ask final questions from sections that I didn't get a chance to talk about in the review videos, like chain rule or limits or one of the other sections.